Okay, I'm going to look at two different experiments that we can do. And you do these yourself. And we'll come back to this first one here and think about it a little more afterwards. But just for the basics here, so if we have a coil and we take a permanent magnet there's no battery, there's no current in the coil. Coil is just a coil. If we take this magnet and we go back and forth, introducing the magnet into the coil and removing it again, you get your needle on the meter will swing back and forth. This implies that the movement of the magnet induces a current. And we know if that's happening, we must be inducing an electric field and a potential, because that's the only way we know the currents exist. Okay? So by implication, we would have a electric field and a potential difference somehow. Okay? Another experiment we can do is we could have two coils. We have to do this carefully, but we can do it. And the coil numbers is determined. So we have a battery, we have switch 1 here, and if we set this up with geometry and enough turns and all the rest of it, because it's a fairly sensitive thing, if we were to cycle the switch, then the current here will go back and forth. Okay, cycling the switch causes a fluctuating current in coil 2. And of course coil 2 has no battery, no power supply of any kind. It's magic. And once again, this would then suggest an induced field and potential. Now, we sit back and say, okay, well, what's happening that at least on the surface be causing this? So, take the second one for a moment, experiment number 2. It's a little bit easier to perceive than experiment 1. Experiment 1 is important. If we close the switch, the current flows, and we have a magnetic field produced in this coil. We know that. And we open the switch and the current ceases, the magnetic field goes down. So what we can say here is a changing magnetic field, a changing external magnetic field induces a current here, because that's the only variable we have. So we could say from experiment 2, a changing magnetic field induces a potential. let's say an electrical potential to be clear. So we could write dB dt is distinct from zero, implies that we get a some type of potential. However, this is insufficient to describe experiment 1 for the magnetic field of the permanent magnet is constant. And so what we have to consider is the same thing we considered back with Gauss's law, and that is the concept of flux, because it isn't the magnetic field in per se, it is the number of how much of the magnetic field is passing through the area of the coil. Okay, so we must advance this to consider the magnetic flux phi sub b this time at the coil. In both experiments, the phi sub b dt is distinct from zero. So we can look at this and say, well, if we're just cycling this coil here, the magnetic field is, coming up and down, and that's going to change the flux here. Although the area is the same, in effect, the field itself is changing, so it changes the flux. Over here, we have a fixed field, but the physical motion of the magnet is introducing more or less of the flux into the coil. So in that respect, you get a constant magnetic field and a changing area. So one is an area variation, one is a field variation. In the same, but it doesn't matter because the flux is what it is. And so recall that the flux then is going to be equal to integral reintegral b dot dA. Sorry, just integral, I apologize. I was just going to say it shouldn't be. Okay? And remember, area vectors are norms. So once again, okay, so this is just to remind us because it's easy to forget. It's an area vector, okay? And the area is perpendicular to the vector. So as we know, when the dot product, when it is parallel, it's just straight multiplication. And the area, if the area vector is parallel to the magnetic field, then the flux would just simply be BA. It would be very simple. The unit of magnetic flux, well, it's straightforward. You would have it's going to be in the SI system, you're going to have the Tesla meter squared. Notice this is not per meter squared, but multiplied. But you'll find no one does this. Everybody retreats to the older unit, which is called the Weber. WB. You know you're a reasonably decent physics student if you know what a Weber is. So if you get to university and you hear people talk about Webers, these people have done a few things. Back in the day, in the early 1830s, Michael Faraday showed that a potential was equal to the difference in the flux dt, and it was negative. And we could add, depending on how you want to do this, so this would be a current loop here. And then we would have minus capital N, oops, dv sub b dt, and this would be a coil of N turns. So mercifully, as we add subsequent coils, it simply multiplies. Now that's a bit of a lie, because as you have subsequent coils, they're positioned in different locations. So I'll lose my rolls of masking tape here. When you say that we can use N, we're implying that these coils are somehow like on top of each other and superimposed, but really they're spaced out. So when the magnet, well, my controller is the magnet, and the magnet is here, it's doing something to this coil, but it's going to be a different flux change to this coil. There's going to be a little bit of difference here. Now, because of the true nature of most solenoids, how the wires are fairly thin and wrapped fairly tightly, there's an averaging process going on here. And of course, they're wrapped and then by machine, and they're wrapped back and forth, and so there's layers upon layers and so forth. So it'll depend on the precision you require as to whether or not it's, how tight you need to know this. Anyhow, so this is Faraday's law, but there's this interesting negative sign here. We should maybe stare at that for a minute and understand why. So I'm going to leave, I'll do the second, actually I'm going to leave both of them up here because we need to look at this for a minute. So, in this case here, the induced current produces a B field opposite to that which induced it. That external magnetic field which induced it. Okay, so this is pushing on this to create some work here. There's an energy transfer, clearly. Okay, and so this is kind of like an electronic version of Newton's third law. This one's forcing, and this one's going to push back. All right, and nothing comes for free, so therefore there's an effort here to make this happen. And the work is done by this battery and all this system here to induce a current over here. And if you were to figure out whatever this took, and you took this away, there would be a different amount here, because this wouldn't be doing the same amount of work as it is inducing a current over here. So, thus, the negative sign in Faraday's law. And that's what this is, of course, so I should have been more specific here. So we'll write it below. And sometimes it'll just be shortened to this, because of course it's a coil, but whatever. And we call this negative sign Lenz's law. It's the only law I know of in physics which is simply a negative sign. So you have Faraday's law, which is the changing flux, but the orientation of that change, the orientation of the induction, is controlled by this negative sign. And so you have here said if we close it, and this is our positive, this is our negative plate, so the current will go this way, okay? And so that means it's coming this way, that means that's our north pole, so this will be a north pole induced. So you might get diagrams on exams or tests, whatever, where you'll have something like this, and they'll just simply say, well, what's the magnetic orientation of the resulting B field? And that's where they like to see if you know Lenz's law instead of a calculation. Now, let's look at this first one for a moment because it's kind of interesting, and this is another one they like to ask you on exams. So, what if the magnet goes right through? What does the needle do? And it's tricky, which is why I'm telling you. And this is a situation where you sort of understand it, but there's a subtlety to it, and some people miss it. So, you're pushing it inward, and it's inducing a current in one direction or the other, okay? So this is north, so that's going to be north. So then the thumb says that's north, so the current's going to come over the top and flow this way, okay? So it flows this way through the meter, whatever direction that would flow, cause the meter to flow, fling, whatever. But initially, as the flux is growing, okay, remembering that the magnetic field lines do this, right? So when you bring it in, the field lines are getting closer together. So that's going to cause the change in flux to be positive and to be increasing. When the magnet gets to here, at any location, the flux stops increasing and begins to decrease. So initially, your meter is, if it was a galvanometer, something where you have your 0 point in the center. As you bring it in, it's going to go one way. As the magnet continues through, and you start to come out the other side, first off, you have your flux starts to decrease. So the meter's going to immediately fling to the other side, and then come back to center again. So it's left, right, left, instead of just left and back to center. So the idea that the flux is first increasing as the magnet goes through, and then decreasing as the magnet leaves, you go, oh yeah, okay, I get it. But it's easy to miss, and that's the stuff they like to look at. Because they'll ask questions like that, so that you might be the person who could write the definition up beautifully. But they'll ask questions like that to see if you understand it. So always be mindful of those types of things. Alrighty. I mentioned that. Okay, that's what I thought. All right. Okay. So induction and energy transfers. And we were, in effect, talking about that a bit here. And for those of you who are on your game, you'll know this is a rudimentary transformer. Okay? But let's not get too far ahead of ourselves. And so, we're going to make a little diagram here. Consider figure 30-8. That's the 9th edition, but maybe you're not too far away. And so we have a magnetic field that's going into the wall, and we have a loop. So our magnetic field is like so. And then we have a current loop like so, which is partly into the magnetic field and we're going to pull it out of the field. Now we're going to be doing work on that to pull it out, and at the same time the amount of magnetic field that is through the area here will change. Therefore the flux will change, and that will induce a current here. So that's what's really interesting about these things, is we have to watch. You get inductive effects in strange ways sometimes, and you have to think about it a little bit. In Hollywood before CGI, this was the king. They could do all kinds of cool special effects with electromagnetism, making things move and stuff from a distance, and all kinds of very clever physics things along those lines. All right, let's get the dimensions of this thing. So again, the field, of course, is this entire region here, okay, not just on the corners. And right. So we'll say the distance, the field's diameter here is B. I see. Okay. Yeah, well, that's right. And then X is there. Okay. All right. And then here we have the amount of coil in the field, which is B units wide. So let's just set the stage here, and then we'll look at what goes on. Our loop has no initial current. Yeah. So the coil, this direction is L. So initially, a region Lx is exposed to the external B field. Okay, it's pretty straightforward. We've got an X width, an L length, height, whatever, and that area then here is Lx, and that's within the bounds of the field. So this part of the coil is outside the field, is not affected. By Lenz's law, an induced potential will act opposite to that magnetic field which began, which started it. In this case, if I pull on the side of this wire and bring it out, then the flux is decreasing. And the field is constant, but the area is decreasing. And by Lenz's law, I'm going to experience a resistance. I'm going to experience an opposite force trying to prevent me, sort of, from pulling this thing out. Now, I suppose if it was high enough, it would do some good, as we'll talk about. The induced current dissipates energy by I squared R, okay, the power of an electrical circuit. As we pull steadily on the loop, And to be clear, we're pulling it to the right out of the magnetic field. We apply a force F at speed, or velocity if you want, V. So the power mechanical power that we're exerting equals FV. It is a dot product, as you know, but since they're going in the same direction, it's a straight multiplication. So we seek an expression for the power in terms of B and the characteristics of the loop. And so this would be L and X and R and whatever we can figure out in there. But these are things that we know. And remember, there's no current flowing in the loop except what is induced. We don't have any battery or anything going on there. So the V sub B decreases as the loop is retracted. As Lx is going down, since X is going down. Okay? And fair enough. A current is induced whose let's not do it that way. Whose induced which, as a coil, produces a magnetic field opposing the external field. So I've said the same thing 3 times, so it should be good enough. All right, so since V sub B is equal to BA, is equal to, in this example, BLX. Okay. And we're going to ignore the negative sign for a minute here just to do some calculations. So we get V is equal to dV sub B dt. This is equal to ddt of BLX. So by construction, the V is constant and L is constant, so it's X that's the variable. And that translates directly to the speed of retraction. So this is going to be equal to BLV. And from Ohm's law, because this is the potential here, then I is equal to BLV over the resistance. That's a small v, not a potential. Now when we,
I have a question.
yes, of course, please.
For V equals like d phi, does it need to be a negative sign?
Yes, that's what I said. I'm leaving the flat Lenz's law stuff out for now because it doesn't serve any purpose. We can stick it in at the end. Because we'll know this opposes, just to make the calculus a little easier to read. Okay? So if we look at this, we're going to have forces on all four sides. And the force that we're going to have, our magnetic forces, are unique to each side. And I'll put in parentheses only inside magnetic field. Okay, so as soon as you leave it, then that's finished. So F sub B is equal to IL cross B. So once again, we figure out our left-hand system here. And this L in this case is the current direction. So we have to figure out how it's induced here. Let's see, to save me thinking too hard. So V goes that way. So this is V in this direction, and according to the diagram, we have a current induced that goes this way, although I'm sure we could figure it out if we thought about it for 5 minutes. So, all right, ILB, just to see if we can decide how these forces work. So we have L, which is going, so it's ILB, so L cross B equals F, so L cross B equals F, right? So let's see, so L going this way, B is into the board, so therefore the force acts, we'll say this force is, the top one is acting this way, therefore the bottom one is acting this way, and this one will act this way. So the top and the bottom here in this example will cancel. They're going to the same magnitude, nothing else is different. So they're going to go, okay? So we have left only with this side to oppose the pull. So let's summarize that, if I can find my chalk, which is here. So F top equals negative F bottom. And they cancel. So F left is unbalanced. All right, so let's extend that then. So F left then is equal to ILB, and we have up here defined our current, and we have, in this case, L works for both because we judiciously defined the length of the wire here as L. It wasn't true on these sides, but it's true on the end piece. I'm going to leave the diagram up. Alrighty, so then we have F left equals BLV over R. Then we have L and B, right? So this then becomes B squared, L squared, V over R. And that's your force. Power is FV, which is then equal to B squared, L squared, V squared over R. And you can see also here, so since P is equal to I squared R, then we would have P is equal to quantity, BLV, over R, quantity squared, times R, and this is equal to B squared, L squared, V squared over R, which is, of course, the thermal energy rate. This, of course, leads to much more interesting things. This is more of a conceptual discussion, but we can quickly extend this. So let's retreat to the diagram here for a second. And let's make it a plate instead of a loop. Okay, like so. And let's think about what's going to happen now. If our, we'll call the topic eddy currents, EDY, sorry. If our loop becomes a plate, and we retract it, we get electrons swirling around in the plate due to the magnetic field. These can be significant. And can, depending on application, produce significant force and or heat. So let us first consider the force example. Being teenagers, I suppose that you have traveled at one time or another to Wonderland to purchase some acceleration. I suspect that that's been part of your retinue. Let me get a longer piece of chalk here. And of course they've populated that location with many more of these metal roller coasters, but there is another experience there called the drop zone. And you have a large high tower. And what you'll notice on the tower are these interesting plates. And they come down like this, and then they broaden like so. And the unfortunates are put in a circular carriage. We'll just draw them somewhere here. So it goes like this, and then you have the folks sitting in this type of a gondola thing. And so they're hoisted about 100 meters up, too slowly. And then the neurotic operator lets you sit there for a few seconds before he pulls the trigger, and you fall for the first bit at free fall acceleration. Of course, the problem with all of this is the sudden stop at the bottom, and insurance officials are disappointed if that stop is too sudden. So we have to have, if you're going to have such a ride, you have to have a mechanism that is bomb-proof, that's going to work every time and twice on Sunday, rain or shine. So friction brakes and all that is just completely out of it. It's not even going to be happening. So what happens is there's magnets on the back of this, and as this thing falls, when you get to a certain point where they choose to that the braking begins, and someone figured out that the negative acceleration you're going to experience here is reasonable for your health, that your innards aren't ripped apart and all that kind of stuff. It begins, and what's happening then is you have a plate here, it's probably copper or something fairly conductive, and those magnets are on the back of those, well, they have these things on different sides of this thing. So as you come against the plate, you induce pretty impressive eddy currents, okay, because this thing is a non-trivial mass. There's probably a dozen people on it. So this is big stuff. And as you come down, the magnet is sweeping across this plate. And therefore, in any particular region of the plate, it's changing the flux very aggressively. And this is going to produce a pretty impressive potential. I wouldn't want to hazard what the number is, but off the top of my head, it's got to be hundreds and hundreds, not thousands of volts. And what that does then, based on what I just rubbed off, is we have a force here that's going to be a function of what's being generated, which is going to be pretty impressive. And of course, these metal plates are exposed to the elements, and this ride, it's probably drop people every 5 to 10 times an hour. So there's time for it. It doesn't get that hot, right? Because it just stops you. So it runs for a brief few seconds, if that even, and then it cools. And you don't even notice that, right? Because you're not close to it. And of course, at the bottom, they have to have some springs here, because when you're not really moving at all and there's no material change to the flux, then this is useless. But it does eliminate the vast majority of the kinetic energy. So there you go. That's an example of the force factor working for real. Now, another version of the concept that I'd love to, whose bugle I like to blow, as I'm always interested in these efficient homes, is the induction stove. So we have first the convection version. Now, I've never understood why induction stoves have to cost any more than convection stoves. I think it's just a matter that we're good at making convection stoves and we don't want to make induction stoves. And I think this is where governments have to step in and say, okay, fine, after a certain year, there's going to be a 50% tariff on these things. And just, you got to change, because you know what, we're smarter now. Maybe at a time we didn't know better, but we do now. So if you take your pot of what have you, and we have suitably a electric resistance element, like so, and when you light it up, and you're making your boiling water, whatever it is, what we'll find, depending on a few basic examples, you can put a lid on it, that does help, but you'll find that an enormous amount of the heat that you're generating just simply goes into the air. If you don't believe me, put your hand over it. So, and it can be, depending on the exact geometry, up to 75% of the heat from the stove just goes right outside, right, heats up the kitchen, goes outside, whatever. It's just completely wasted. If we use an induction stove, and we use it properly, which is another discussion, now we take a pot like this one, and this must be ferromagnetic. So no aluminum. It doesn't do any good. Okay, you have to have ferromagnetic. So stainless steel works great because that's a nickel steel thing. You got two ferromagnetic materials in there. You can't miss there, right? So, however, what I would recommend is we insulate the outside of the pot with some kind of porcelain material, whatever you want to make it pretty. Lots of nice pictures on it and stuff. And then we have our coil underneath here, and like so, whatever. And what we're going to do with the coil is sort of like one of the first experiments. We're going to simply cycle it. Magnetic field will be constantly pulsing and changing direction. Maybe just through the standard alternating current from the house or something like that. Cycle, cycle, cycle. Now what this is going to do is produce eddy currents in the steel part of the pot. The porcelain is irrelevant. the steel part of the pot will get hot. The whole thing, not just the bottom. It might be the bottom gets a little hotter because it's closer, but the sides will heat too. And you can put a lid on it, it's the same as before. The stove remains cold. You will not feel, you can touch the stove, especially when you're using an insulated pot. If you're using a metal pot, the stove will get warm because of conduction, so you have to be careful. But if you're using an insulated pot, which I would certainly recommend, then the overwhelming majority of the heat is going to be contained in the pot in heating your oatmeal. And you could save, depending on the exact geometry of this, half the price to 3/4 of the price it costs to heat up your stove. This can be done also for baking and other things too. When we have the oven, we're heating the air, which is one factor, but we're also heating the pan where we're making our cookies. One of the challenges of making environmentally friendly houses is the heating, the cooling, and the stove, and the heating of water. A lot of the other stuff isn't so bad. Lighting with diodes and light pipes and stuff is all pretty simple now. But the stove, this is a world beater for the stove, because we can use this energy, and it doesn't take all that long to heat a pot like this, and we can save a substantial amount of energy. Our kitchens are one of the worst wasters of energy in what we'd hope would be environmentally friendly homes. But I talk to people who say that an induction stove costs $2,500. And I know when I bought one, a half decent in convection stoves is like $1,000 maybe, if that. And that's like an oven and 4 burners or whatever. I cannot for the life of me understand why this technology is any more or less than the other one. I just feel it is some kind of industrial thing. And this is where I think governments have to step in and say, look, this has to change. Because where do we use our energy? We're using it when we produce heat like this. And if we're doing to produce heat, let's produce it where we want to produce it, not just because we're too lazy or, 1925, I get it. But this is 2025, so to speak, and we shouldn't be using the data technology, especially when our world is as much trouble as it is environmentally and so on. Okay, speech over. Induced electric fields. I've always had this dream that one of my students will do a graduate school project and have a couple of houses built where the house is off the grid. And now this is not a house that costs $2 million and is made for yuppie type people, but it's a house that's a modest cost that works for the every person. We're going to solve our own problems to some extent like this. A lot of people in our society would like to make better choices, but they don't really get a chance. We are forced to plug into our society. We're forced to plug into the utilities. We're forced to do these things. And I understand that some of it's done for our safety. But what I'm trying to say is, if we can use our technologies today to make these a home where the loop is almost closed, and we don't need the public utilities anymore. We don't need the hydro system. We still have power. We can make our own power, and we can heat our water. We can take our water from the environment for the most part. And I think that I would love to be invited to that site and see what they come up with. But like I said before, anybody can throw millions of dollars at something. I'm looking at using clever methods, giving up a little efficiency here and there, but doing it with basic good common sense. And I think maybe we'd be onto something. It'd be great fun to see that come about. Okay, let's see what this is telling me here. We already know this. If we place a copper ring uniform magnetic field. We then increase B at a steady rate the flux, I'll just put here a steady rate, causing phi sub B through the ring and it's a radius r, of course, to increase as well. From Lenz's law, or well, from Faraday, and Lenz, we end up with a current in the ring which opposes the external B field, which we know this. That we have a current implies we have an electric field. So a changing magnetic field begots an electric field. And this is something we will begin to become aware of, is that these two phenomena are interconnected, as Maxwell taught us so well 150 years ago. If dB dt goes to 0, then the electric field will disappear. And the current in that ring will stop. So, note that the remaining magnetic field may well be significant. However, as long as it is dB dt, or technically the phi sub B dt, which matters. Now you could be damn sure in contests and exams that they're going to take you to task for this. This will be the one thing, and they'll set things up and they'll have a B field equal to that of a neutron star, and you have to realize if it's not changing, and then more important, the flux. So you might, well, the field's the same, but we're lifting this thing off the surface, and you recognize that's going to change the flux, and so there's something going on, right? So the work done in one rev of the loop first we have, let me just get, yes. So we have the energy is equal to, so we'll just say U sub E is equal to Q naught times the potential. Then per unit charge, which is what we seem to care about more, we have work is equal to the integral of F dot ds from mechanical physics, which in this world is equal to Q naught E times 2 pi r. And then the so then V, we just forget the Q, okay, is equal to 2 pi RE. So there's the connection between the electric field and the potential that's been induced. Also, the potential is equal to the ring integral of E dot ds, technically speaking. So we can reformulate Faraday's law and this was work done by Maxwell, I think. And we have V is equal to the ring integral of E dot ds is equal to negative d phi sub E dt. And then, so that would depend, that this can be quite an interesting expression. Well, so we've got this E dot ds integral now, where before we just had the potential, okay? So this is more of a finer version of it, and this can be shown from this ring argument here, which is kind of neat. Okay, let's see, we got, that doesn't matter. Okay, inductors and inductance. Let's just play with this for 5 minutes. So an object known as an inductor is one which can produce a desired magnetic field. We shall consider a long, thin solenoid as our basic type of inductor. So inductance is capital L N phi over I. This is the definition of it. And when you first see this, it's confusing. But hopefully it makes more sense in a little while. So N is of course the number of turns. Again, it's a capital, so usually it's a total. And since these turns are linked, N phi is the magnetic flux linkage. Well, this all makes, it's new fancy words, but it makes quite good sense. So the inductance is a measure of the flux linkage produced by the inductor per unit current So if we look at capacitors for a minute, which are maybe a little bit easier to appreciate, you're putting charge on the plates. And for a given potential, if you can put a certain amount of charge on the plates, and you can do it with less potential, then the capacitor is more efficient storing charge. So the capacitance will be higher. So that makes reasonable sense. Well, let's look at our inductor for a second here. So where we are over here. So we can produce a magnetic flux here, which is fairly impressive for less current than the inductor is more capable. Okay? So for whatever reason, its geometry, circumstance, however it's designed, if it can produce a greater magnetic flux for a given amount of current, then we've got a better inductor. Okay? All right, now let's just see where we can draw a line here because we're getting near the witching hour. Yeah, let's do a little bit more and then we'll call it a day. So based on L is equal to N phi over I, then for units, we would have, so the unit of magnetic flux is the Weber, right? And N doesn't have a unit. So we're going to have Webers per amp. And this is given one of the better names in physics. This is called the Henri. And it's capital H. And so, okay, so that looks like that's working. And
wait, maybe since Soviet Russia, geez, it's time zone, it's not time travel.
yes. Well, the same location anyway, so they're on, they use double daylight savings time over there, so, because I guess it's in some of those areas anyway. Okay, now we need to plug in the webcam. Let's see if that worked. It did. Okay, so let's make that high def.
Hello.
I think you're teaching right now.
I am about to, yeah.
Okay, is Sarah Alley in this class?
Yes, she is.
I've been trying to get her to find out if she's paid for her AP from every avenue I know.
Okay.
And so I just realized if I pop on right now, I
All
can talk to her.
right. Sarah, can you activate your microphone, please? Sarah Lee, hello? Yes, it's Ms. Hermanowski. She wants to speak with you.
I have been trying to get in touch with you. I don't know where the camera is on this thing. Anyway,
I'll
can
switch
you
it over.
please check your email? I need to make sure that you paid for the AP exams, and maybe you paid under someone else, but if you, I am waiting on you. Well, I don't know where this camera comes from.
Right there.
I'm waiting on you for me to be
Jackie.
able to send it out, okay? So, check your email right now. Email me back, send me some sort of evidence if you did pay and I didn't see it, or if someone else paid. And just let me know, because that's the last thing left, okay? Thank you. Bye.
Mr. Rogowski.
Yeah.
Sorry, I just have a quick question.
Yeah.
So my dad said he got an email from School Page Online saying there was an AP exam this year, so he paid for it, but I'm not taking any. So I
He
don't know
paid
if
for
it's a
it?
mix-up.
But did he physically pay for something and
I
actually?
got that too, but I paid for it because he thought I was taking an exam. And he just didn't ask me, but then afterwards he told me he did.
Oh, okay.
But I don't have an exam. Is there a way we can like?
Yeah, we can reimburse that, definitely. So it's like, so Jackie, you did that too? This is such a trippy.
Well, just because I'm about to talk, that's why I bring it away
Got
from
it.
here.
Sorry, Jackie, you too? You got the email and you paid, or you just got the?
I got the email, but I didn't pay for it.
Phew. Okay, Sophie,
I
that's
think I
legit.
told you about this.
Yeah, that's a legit problem. So we are going, you email me that to remind me, and then I am going to tell whoever is the new Miss Ali to
Yeah.
to reimburse that. So
I think
we're-
Bruce is going to do it.
Bruce? Okay. Yeah, email me, because yeah, if you're paying for something because your dad was just like, okay, I guess I'll just pay for this.
I wish I had a father like that.
Yeah, I
That'd be
know.
okay, yeah.
140 bucks, okay, no problem.
Just
Whatever
need
Sophie needs.
I need a thing for my car. I could do that.
Okay, bye everybody, thank you. I knew it. I was like, this is how I can get to Sarah. That's how I'll get to
She
her.
just wanted to spend time in the physics lab. That's all it is.
Yeah, you'll notice, Sarah, like I emailed you 3 times. It's on the TOPS discussion platform. I got Cynthia to text you. It's very, now I can get rid of all those avenues. Okay, thank you. Bye-bye.
See, this is what I was like last year, and
Right? Like chasing TOPS kids down.
I left a present for you
Where?
in your room.
I got the chocolates?
Yeah. I don't know who the hell gave it to me, and I said it did so good to me.
I thought it was Michael then.
The chocolate always works. Did you see what else I left for you?
Like something about like a leaf?
Yeah, look on your.
I saw it, but I thought it was Michael, so I just ripped it off. He brings it all the time. What does it say? Big leaf.
Oh, on top of the. But it's covered.
Oh!
It's no fun if you don't get the joke. Jeez.
That's so good!
Angela
You
Chan
put it
thought
over their lungs.
Angela Chan thought it was
But
funny.
you put it over the lungs, Henry.
No, I didn't. It was down. Well, Sony moved it then.
In the nether regions.
Yes. Yeah. They're listening.
I got it. Both of those crates are exactly Michael's style, so I would have appreciated it now that I know it's from you. Because I was going to text Michael and be like,
My old Smith.
Yeah.
Oh yeah, he's harmless. But
Yeah.
he looks like he's a nice guy, but there's a streak in him.
The thing is,
He's
you think chocolate is harmless until your 30th chocolate bar, and then it harms
If
you.
you run.
Yeah, Henry, only eat half a chicken at Swiss Chalet.
But the problem is, I walked to the GO train yesterday. I walked 12K yesterday, but then I go to Swiss Chalet and I ate more. Like it's stupid. Yeah.
Oh, God, I know.
See ya.
Okay, have a great weekend.
Okay, so you can see how much fun teachers are. All right. So let's pick up from yesterday then. So we had defined the inductance, which is mercifully, that's right above us here. I've got my recorders on. Yeah, I think everything's working. Okay. So I'm going to take this stupid mask off because we don't need it. And this is not me being political. I'm all by myself in the room now that she's run away, thankfully. So inductance of a solenoid. So we just introduced the concept of inductance, and this equation is weird. And when you first see it, you go, what are we doing here? And I don't blame you. When you first think of it, and as I kind of explained it to you yesterday, I said, this is the flux linkage. So this is the amount of flux times the number of loops. So there's a certain amount of flux, magnetic flux in the coil. Now, if this is produced by a smaller current, all right, as we know, magnetic fields, magnetic flux is generated by by currents, okay? If it's produced by a smaller current, then thus the device has a better capability of producing a B field with a lesser current. Hence, the inductance then, the property that way, is greater. So that's probably the best explanation after 20 years of doing this that I've ever been able to manage. So anyhow, there you go. So inductance of a solenoid, and so let's see now, where'd that go? Oh, there it is. So we consider our long solenoid. It has a cross-sectional area Now this is the area itself as a value, not the area vector. We'll see if we need it. And and so what is, oops, let's do it over here. What is the inductance L over, I'll do a script L, and in parentheses I say the inductance per unit length near the center. Now it is a bit of an interesting concept to deal with inductance as a function of length versus just the inductance, but if we get this we can also figure it out as well. Well, let's see what we can do here. So the flux linkage of the solenoid is going to be equal to N script L VA. So N, and just pay attention here, it's not hard but it's new. So N is the number of turns. Lowercase n is the number of turns per unit length. L represents the length, hence NL equals big N, right? And the flux, because the magnetic field is parallel to the area vector, is simply just magnetic field times area. So, you know, if you need to, make a note or two so you'll understand where this stuff's coming from. And oftentimes that's a good way to test if you understand the concepts. Just having all these coils together, okay, is just what we call a flux linkage, because the flux is linked between the coils. Just like you saw when I did the solenoid originally, you have the magnetic field goes through them all, not through them individually, and so they're kind of linked by this magnetic flux. So that's where we're coming from on that. Alrighty. Also, recall that ominous word, B is equal to mu naught I small n, and that's for, of course, the solenoid. And that's near the center and all that. So then, L over L, sorry, that's my misspoke, L first. L is equal to N phi over I, which is equal to N LVA over I, which is equal further to NL mu naught IN times the area divided by I. And notice here we have an I on the top and the bottom. And the inductance of a solenoid or whatever should not depend on a particular current, right? It should depend on the device's properties, its area, and so forth. So this is a good thing. So then L will be equal to mu naught N squared LA. And then L over L would be equal to mu naught N squared A. And so in this, we want to look at what matters here. Okay? So, star, exclamation mark. So, N, the linear density of the windings. Is paramount. So you might see in some type of a science fair project or something that someone's made in their garage, you might see something like this, where we have a coil, like a transformer you might be able to see. So the pipe, so we got a bunch of turns, sorry, not a transformer, but like 2 coils. And then they'll just have the coil go like this, and then there'll be a bunch more turns here. And you think this wire matters, but it doesn't, right? Because the N, the small n here is quite significant. It's irrelevant here, and it's significant here. So these are separate, in effect, separate. They're linked because they have the same current, but other than that. So this could have way more turns than this one, or whatever. It doesn't make any difference. They're separate. So you see those times these rigs, and that's why you can do this, is because it's a function of n squared. So here we have, let's say 50 turns per unit distance, whatever that would be. That would give us 2,500. Here we have 1, so that's 1. Then we have maybe 30 here, that's 900. So the inductance here and here is quite significant, and here it's irrelevant, as an example. Now, of course, it'll depend on what you're doing and how much of the inductor you're actually dealing with, as into whether you were to use this or this. And that depends, of course, on the application. Self-induction. So these two ideas are confusing, and you're going to, and whatever I try to do here won't be enough. You're going to have to stare at it a little bit. And the textbook would be where I'd start. So let's write this carefully. If 2 inductors are proximate, a current in one coil, so I'm using coil and inductor interchangeably, produces a magnetic flux through the other. However, because this is a steady current, the magnetic flux is fixed, and other than the transients of when it is initially set on or turned off, there is no potential, no induced current in the second coil so far. If I is changed, then V sub B is changed in coil 2. And we have induced EMF. I haven't used that with you, so I'll do this one. Electromotive force, or just, potential difference, whatever you want to do. Okay. And this, of course, is pursuant to Faraday's law. so far so good. However, this fluctuating current will produce a potential difference in the first coil. And this will oppose the current. Now this is really just, like I said earlier, with Lenz's law, Newton's third law for electromagnetism. So it's more of a different expression of it than it is anything new in concept. If we have a potential difference showing up in the coil due to the induction of the second coil back onto the first coil, that's the same thing as a force acting against it. And our power supply, or whatever we're doing to drive this, would have to be sufficiently strong just to push through that. So, then N phi is equal to Li, and this comes from the definition of induction. We still have one on the board here. We can just take the I and put it over here, so we're not doing anything too exciting. From Faraday's law, we have, we'll back this around, so ddt then of N phi, okay, is equal to a potential difference. So we can say electromotive force, we can say, and then that's equal to V, which is also equal to, and then we have L di dt. So once again, the potential doesn't change, doesn't show up if you don't have a changing current. Okay, and this expression here will matter later on when we do inductive circuits. Okay. Well, it's going to matter right now, actually, because we'll do RL circuits. So consider the circuit. So we can have a battery, supposedly, and a resistor, and a coil, so, and we can set it up if we want to, having another wire here, and making this a switch. So whether we induce, put a current and induce a B field here, or we turn the switch off and let it bleed away. So once again, just the same with RC circuits, we don't have a instantaneous charging the capacitor, and we don't have an instantaneous development of the magnetic field. They're exactly the same kind of situation. So for an RL circuit, the magnetic field is not produced instantaneously. initially, so we're going to have we don't have to do work to make this field. There'll be a potential difference here. When we're finished producing this field, all you'll have here is the legitimate ohmic resistance of the coil, which is going to be comparatively trivial. So initially, we will have a voltage across the inductor. Later, V sub L will only be the ohmic resistance of the coil wire. So V sub L only appears when we're changing the current, and you see that here in this previous derivation. We saw the differential equations when we had an RC circuit, which we just tested on recently, and we now face a similar situation. So then, for charging or energizing, whichever you like, we have V sub L plus V sub R equals V of the, we'll say V of the battery or whatever you're using, okay? So now we're going to enter the definitions and see what we find. So V sub L is going to be L di dt plus IR equals V sub B. Now, in this case, we're going to look for the current, so we don't have to mess around. Whereas in the capacitor, we looked for charge, and then we had to take a derivative later on. But in this case, we can look for the current alone and just simply deal with the differential equation. And so we end up with di dt is equal to, plus I R over L equals V sub B over L. I'm not going to worry about the, we've done enough of this. So 3 dots, I would equal V sub B over R, 1 minus E minus R over L times T. So let's see what that means. If the time is infinite, then this exponential term vanishes, so we don't care, and we would have simply the ohmic resistance of the circuit, R being the circuit resistance, which is the resistor if we assume the coil doesn't have resistance, but you could add it if you wanted it. As when we first start this at 0, okay, the current will be 0, but as time starts to tick on here, okay, the current will slowly increase. And because again, we're doing work as we build the field. If we turn off the power supply and short the wires, it goes the other way, in which the coil tries to maintain the field. If V sub B equals 0 and the coil magnetic field is energized, then we have L di dt plus IR equals 0. When you're done, you get I of t is equal to I naught e to the minus L over, let's see, t sub L. R over LT. So as this increases, okay, this gets smaller, and the current becomes just the ohmic current, right? Basically, this is the same as V over R, right? Now, you'll see in chapter 31, when we have alternating currents, the capacitor and the inductor and the resistor will work out of phase of each other and cause oscillations. Okay, and we'll see that. I might do just a little bit of it to show that to you, but we have to see how much time we have first. Energy stored in the magnetic field. If we take two long wires with parallel currents, they will attract when we derive this. So I'm reminding you more than anything. It takes work to separate. We seek to we seek to derive an expression for this as it is a design constraint. We have V is equal to L di dt plus IR, of course. And we could multiply through by R. Let's do that on the next board. Now let's think about why we might do that. So we look at these terms. It's not immediately clear for one of them, but the other two. Multiplying by current here, I get I squared R, that's power. Multiplying potential by current gives me power. But this is kind of a mystery. We think it's power, but it's it's not something that we're very familiar with just yet. So we have IV is equal to Li di dt plus I squared R. And so these two are power, dimension of power, right? For IV or some right DI. The reason they make a point here of the electromotive force is that the battery has an internal resistance, which is fairly small. But if you do it, but it does change the difference between what the battery is really doing and what you detect outside the battery. This is a distinction that's not normally bothered with in most situations. So, summarize. Okay, so for this, it is the rate at which electrical energy
Question?
please.
Can you explain where you got the initial expression of potential from?
Now, where am I looking here? This one?
The V equals, yeah, right there.
That's from the differential equation we just did 2 minutes ago, an RL circuit?
Oh, okay, so in the RL circle.
Yeah, okay. So, and again, Arthur, we know, we're talking about what the energy stored in the magnetic field, so we're still within the context of an RL circuit, right? So we're talking about the energy stored inside the solenoid in an RL circuit is what we're really saying here, okay? So, electrical energy does work in the battery per unit charge. So that makes sense. We know this is the rate of dissipation of the resistor, so we don't care about that. So then, we would say du sub B dt, which is equal to Li di dt. This is, of course, I'm going to say, instead of B, I'm going to say L, in the sense that the energy in the inductor, because that's what we're interested in here. And we can integrate, so if we cancel the dt's, right, we would have du sub L is equal to Li di. If we integrate u sub L is equal to the integral of du sub L is equal to the integral of Li di, which is equal to 1 Li squared, 1/2 Li squared. For a capacitor, we have, yeah, I'll be right with you, u sub c was given as q squared over 2c. So the energy expressions are slightly different. Sarah? If it wasn't Sarah, who was the question?
The expression at the top of the left panel. IV does not equal I squared R, right? Like the different values in this circuit?
Yes, that's quite true. This is the throughput of the battery, the energy added to each particle. This is the power dissipation from the resistor in the circuit. This is the energy of the magnetic field, if you will, that's being used by the coil. Does that make sense?
Okay. Yeah. So then how did the algebra work out to get dul over dt?
So what we're saying here is this is not an energy, this is a power, right? This is the power of the entire circuit. This is the power of the resistor. This is the power dissipation use, whatever you want to call it, of the inductor. So we have this down here, and so this is dimensions of power, and by definition, U sub L, which is just electrical energy, is dUL over dt by definition, right? The power, I mean. Okay?
Yeah, okay.
So that's 112. Okay, that can go back. And I did that. Where did I? Oh yeah, okay, I see now. So then the next thing we did was energy density. Of an inductor. Now you might wonder, this concept of energy density seems a little weird, but let's just think about for a moment, just to put it in perspective in a different way. You take the batteries that existed, you've got the cheap batteries, the carbon batteries in the store, maybe they'll make them anymore. Then we have alkaline batteries, then we had NiCads, and ultimately the newest flavor is, of course, these lithium-ion batteries. And what you'll notice is that, maybe we want to go as far back as lead acid even. What we're noticing is the amount of energy you can store per volume and or per mass is getting much, much greater than it used to. And so the ability to store energy in a particular volume is of great interest for all kinds of applications. Now, I've talked at some length about spacecraft and how we have to miniaturize, but we can take a lot of electronic instruments, medical instruments, and things like that where space is at a premium, and or the other things that you're trying to do means that all of this has to happen in a fairly small location. So increasing the density or being aware of the density of the energy and some of these components can be very, very important. Now, of course, this is just the beginning, I understand, but still. All right. So we have a short length script L of our solenoid near the center, to be clear. The volume associated with this is, of course, A times script L. The energy stored in this region, or in this length, let's say, must lie in this volume for B external is effectively 0. The energy is expected to be evenly distributed as the magnetic field is uniform. Hence, mu sub B is equal to big UB over AL, which is just the definition, the energy by the volume. And then we would have 1/2, so we would have Li squared over 2AL by substitution. And we might also have L sub L, mu sub B is equal to L over L, I squared over 2A. And of course, L over L we already know, and we just did it a minute ago, but for information, L over L once again is mu naught n squared times A. So if we were to extend this, then you would have mu B would equal, so this is this, so the A's would cancel, and you would have mu naught n squared I squared over 2. So the density of the energy, as you might expect, is going to be dependent upon n squared, because that's the inductance, but it's also going to be a function of the current, which is going to drive the magnetic field proper. That's left here. So did that, this, or mu sub B can be equal to the magnetic field squared over 2 mu naught. Also can happen. And recall we had mu E equals 1/2 epsilon naught times the electric field squared. So what we're noticing is a little difference between these two, but that's okay. Finally, we have mutual induction. I'm going to do this a different way than the book does. I find this confusing. I don't know how much it helps. Suppose we have two coils. And we link their cores with a ferromagnetic material. So it might look like this in just rudimentary description. And we deliberately put a different number of coils around either side, but this says that the magnetic flux will cycle. Okay? We'll say this is iron or something like that for now, steel or whatever. So the magnetic field of the initial left side, let's say, will be maintained and sent around. On the left side, we have, and we'll just use the original version of Faraday's law, we have V is equal to minus N dV sub B dt. And we have, so whatever phi is going to be, okay? So phi of t will be some oscillatory function, whatever it's going to be. Generally, we'll use a periodic function, like the electrical circuit or something. The flux produced on the left be the same on the right. Okay, they're linked because of the iron core. You can do it with air, it just doesn't work as well. So having the cores done like this works quite nicely. And you could even use that pipe version I showed you earlier, would work the same way. It doesn't have to be complete, it's just more efficient because the field will continue all the way around. However, the induced V on the right is proportional to N on the right. And so we can set this up very nicely. If our signal, if Vn is equal to V naught sine omega t, okay, on the left, then we'll just say V left, V sub L, say here. And then V sub R is going to be equal to sine omega t, but the flux that you're going to get will be the same, but you're not going to get the same voltage because it's proportional to the number of turns. So we have N2 and N1. And so VR is equal to N2 divided by N1 times VL. And for peak value, so this is continuous. So for peak values, which is what we often will consider, you get V2 equals N2 over N1 V1. And this is the transformer equation. Now, back in the 1880s, 1890s, there was an enormous debate in the technological world, primarily between Thomas Edison, the famous inventor, the Wizard of Menlo Park, and a less known inventor who is one of the good guys. His name was George Westinghouse. Now, of course, Edison is famous for inventing the light bulb, and good for him, 1878, 1880. But Edison, as much as he was one of the, probably in my view, is on the level of Da Vinci in just technical genius, and I think there were others, but I mean, he really was pretty good. But Edison had very little school, and so the developments of electrical technology, especially alternating current developments that led, of course, even in our work here with some calculus, were well beyond his education. That's not saying that Edison ultimately couldn't have learned it, it's just it didn't happen and he wasn't inclined to be a book learned. He was more of a experimental genius. Westinghouse himself had more education, had been a Civil War veteran and all the rest of it, but he ultimately ran into Nikolai Tesla, the brilliant Romanian physicist who had come over, and Westinghouse, whose main aim, you'll see there's comparatively few pictures of Westinghouse because he was not a showman. He wanted to simply do the right thing, and he would often let other people take the credit. It's really a shame that there isn't a first-class museum of Westinghouse because he deserves it. There are more patents coming out of Westinghouse's situation than there were out of Edison's, but you wouldn't know it based on the horn honking that goes on, primarily because of Henry Ford, who was a good buddy of Edison's. Now, I'm not saying that Edison deserved it. He was a remarkable individual, and there's no question about it. He was also a pretty tough customer, and he was probably pretty vindictive. So what happened, of course, is the short answer is, not to make this too long a story here, was Edison, of course, had invented the electric light and some other devices, and he knew, of course, that we had to now produce electric light for the masses. And the idea that everybody would have an engine running in their backyard to power their house wasn't practical. And so he wanted to make generating stations that would then supply the power to the homes. The problem was Edison only understood direct current, and he wanted to make DC generators, but to make them work, because it's very, very difficult to change the voltage of a DC flow after it's been set up. We do this today a little bit, but in those days that was difficult. Whereas, as you've already seen here, we can change the voltage of a, this could have been an AC circuit coming in here, and going out the other side would be a separate AC circuit, would be the exact same waveform and phase except a different amplitude, and hence a different voltage. So what that meant, and we also know, as we transmit across fairly significant distances, is twofold. One is we have big long lines, so you want to get the voltage as high as you can, so you reduce the current, because we know that the power dissipation is I squared R. Okay? So the idea would be power generation somewhere, raise the voltage to high, thousands of volts, maybe more, transmit it as far as you need to, and then step it back down to safe levels so it can be used by the consumer. And this was what Tesla had in mind, and it's what we still do today. And in fact, you've got these little power supplies to plug in. Now the technology has changed, but for the longest time those little brick things you stuck in the wall to power a device were simply just miniature transformers. So they would take line voltage, which is lethal, drop it down to the 5 volts or whatever it is your cell phone or your calculator or whatever it is needed, and off it goes. Sometimes if you have a DVD player or something like that, you plug it into the mains, but inside it there's a step-down system. And so this was so easy. If you go around your subdivision, those green boxes on the lawn, that's what they do. They take the power from the poles and they'll distribute it amongst 3 or 4 houses, and then the next 3 or 4, because you need to drop that power. If it's not on the poles, it's underground, whatever it is maybe, I don't know, but it'd be 10, 20,000 volts, maybe more, to be lethal, of course, in the house. And they drop it down to 208 volts and then run it into the house from there. And now, in our subdivisions, we do this all underground, so we don't have the unsightly hydro poles and all the rest, where before we didn't worry about that. So this ability to very quickly and easily and without moving parts, so these are very reliable devices, change the voltage of AC, meant it was going to be very versatile. We could move it around very easily. DC, you can't do that. Now Edison had been the big dog for a long time. He invented the light bulb, he invented the stock ticker systems, he invented the phonograph and a lot of the initial film industry. Even though he didn't invent the projector, he certainly did modifications to it, and a host of other things. And along comes Westinghouse and his friend Nikola Tesla, who of course understood the calculus, and as a consequence Edison felt the heat, and he felt that he could be usurped, and he wasn't about to give up his place at the top of the food chain. And so Edison, using his movie systems, tried to scare people. He invented the electric chair. He would electrocute animals and to make movies of them and show them in the cinemas before they saw the feature film, in order to scare people of these high voltages. Now Edison may well have been somewhat justified to be afraid of the high voltages, because one of his first inventions was the rat paralyzer, where he had about 1,000 volts between 2 plates. When a rat came out of the rat hole, it got it. But I think that's probably too generous, because I think he was also interested in trying to make it for himself as well. Anyhow, this went on for a while, and by the late 1890s, the War of the Currents, as they called it, was won in favor of Westinghouse, which was the only way you're going to do it anyway. You're not going to have power stations every half a mile, silly. And they reduced power at Niagara Falls and transmitted at 97 miles and so forth, and all of these types of things. And this, of course, so Edison, his company had been called Edison General Electric. And after this, the board of directors took him out of the company. They took his name off, that he was no longer suited for this. And so he left in a huff. He bought a mine and he learned how to crush rocks and did some innovative things there. He invented the prefabricated concrete building and all kinds of things. He's a remarkable man. But Westinghouse, whose name is now on occasion in certain consumer products, is forgotten for this profound contribution. So the generating system is based on his ideas. And it's quite a wonderful story about him. And that, I suppose, is enough for induction. So what time we got? I think it's a Friday.